Okay, right. And second equation is going to be 1 minus 2i times y2 plus then a quarter of all that stuff we found earlier. Okay. With all of that, what do we have here?
It looks like a differential equation.
And each of them individually look like what kind of differential equation?
Well, first order. I'm being. I mean, again, I'm sort of like.
I wasn't talking to you.
Okay.
I'm mouthing off at Excalibur, but yeah. So these are first order, and also.
Well, they're not separable.
Nope.
But you can solve them by integrating factor if you wanted.
Right, because they are first order.
Linear.
Linear. Right, so by order, or by virtue of the fact that these are now first order linear differential equations, we can solve them separately because we've done this before. This is, I will say, really gross in terms of like, there's a lot. Let me pull up Drive. I don't want to do it in that window. Let's pull up Drive over here. This is 2020-08 FA260. Wait. And there we go. 101501A. Come on. Promise I do actually want to open this. Alright. Alright. Let's show this off because it does get a little much. Recent pictures. Screenshot. Alright, so this is my work from 2020. Which I did after class because I told my students I was not going to do this in class. So I just worked on it like in my free time between stuff. Provided it decides to work. I mean, I know, Zach, you said earlier we were hitting the limit of Excalibur, but at the same time, I usually can post a picture no matter what.
Yeah, it happens.
Alright, maybe we'll break the share. Yeah, there we go. Should be the same, but we'll see. No, they changed it. Okay. Oh well. So yeah, as anybody who's in can see, this is getting a little much. In addition to the fact that I just write small when I can. We're separating out the differential equations. We end up with our y1 and our y2 here. Eventually we get to the end, and then we say, oh, by the way, x is going to be t times y, so now we take our t matrix, 2i1, negative 2i1, and multiply by the solutions to the y's we just found. And then when we boil it down, it does end up with negative 1/5 e to the negative 2t plus e to the t plus 2i times c1 plus a bunch of other stuff. In this case, it's c1 and c2 with the e to the negative 2t and e to the t. Nope, sorry. E to the lambda 1 and e to the lambda 2 that we had from before. C1 and C2 in this case are just imaginary numbers, which knock all of that stuff back to the reals. And then at the bottom we have 1/5 e to the negative 2t minus 1/2 e to the t plus C1 times e to the lambda 1 t plus C2 e to the lambda 2 t. And again, this is the null space solution. So we know from earlier, right, we're just going to get our x vector is going to be equal to our null space solution, which we said was this stuff here, plus the bits that we found here. So the matrix diagonalization method ends up finding you all of it all at once. You may have to do a little bit of cleanup at the end, and it doesn't get you the sine and cosine version unless you really go into it and, like, you know, separate everything out and break all the pieces into their appropriate parts. And eventually you end up with your e to the t cosine and e to the t sine of 2t. But it, as you can see, it takes a while. So it might not be your favorite thing to do. I don't blame you. Zach, do you have any comments on matrix diagonalization?
Matrix diagonalization is really helpful, especially when you use eigenvalues. I mean, when you take e to a matrix, I don't know, like I said, you want to go into this, but basically taking e to a matrix with something diagonal is extremely nice, and that's what makes this whole thing possible. Really. So if we didn't have nice matrices, things would have gone very poorly. Or, like, you know, if you don't have that diagonalization done, then bad things happen. I don't know. I'm speaking gibberish right now, but basically, like, I've done enough of these problems that it can get messy. There are other methods to solve these as well that I know you'll. I was looking at your syllabus, and I know you're going to get to those things, so I don't want to say much about them now. But yeah.
And likewise, if we end up with no, that doesn't have it in it. Cool. I'm gonna start speaking gibberish too at this point. I'm okay, I promise. Right, so when we start looking at matrix diagonalization, I personally much prefer doing this with technology. I didn't really want to do all of this stuff by hand, especially, you know, coming up with our null space in terms of sines and cosines. Like, if you do it with the fundamental set method that I talked about at the beginning of this class, then it's not too bad, because it's fairly easy to just say, okay, well, we need all of these portions, and so how do we get those portions? Right, e to the t sines and e to the t cosines in some arrangement, and then figure out what that's going to be. Okay, so we have our method of undetermined coefficients. We also have our matrix diagonalization method here. And is that here again? It's very strange. I must be missing something in my notes here. I'm sorry. This is a bit strange. Alright, we'll just do this one because it's cool. Good a reason as any. Alright, so x prime is going to be equal to, let's do, yeah, 1, 2, 2, 1 times x vector plus really? Sine of t, t. Alright, how do we work with this?
Again, you get to sort of choose your method. So which way do you want to slice this?
So how would you go about doing this particular one, do you think? And why?
Well, I would look at its eigenvalues, and those would form my homogeneous solution.
Mm-hmm.
Right, like the eigenvalues and eigenvectors, slap on some C1s and C2s. That would give me the homogeneous solution. Once I'm done with that, I can compare what's going on in the non-homogeneous part and know whether I need do something. What I need to adjust by, if anything. But I doubt I will, because I have a polynomial and a sine of t. Those belong to sort of two different classes of things. So I'm not super worried about it. But we'll see. Who knows? There might be an eigenvalue which would throw things off.
Alright, how'd you like to solve the characteristic?
I'm doing it in my head. That might be my famous last words. But you're going to have 1 plus or minus 2. So what, 3 and negative 1 are your eigenvalues?
Alright, how'd you get it?
Algebra. Like literally just solving the,
So did you knock this into a second degree polynomial?
Well, no, actually I just add 4, complete the square style. So add 4 square root, making plus or minus 2, and then move things over appropriately.
Yeah. This is one of my favorite things.
Needed.
Yeah. This is one of the favorite things to do with a lot of these students, is that they're so used to like saying, "Oh, I need to expand this." And it blows some of their minds, not many, but some of them, to say like, you could just bring that over and say, what do you need to do? Most of my pre-calc students have generally seen, things like this, because I wanted to say like, what's the easiest method to get to a solution? Now also, what are many other methods that somebody else might have done? So we can see that there are multiple different ways that really end up getting the same result in the end. I know you're all about that.
I do enjoy having different ways of doing stuff, that's true.
No. So when we take the square root of both sides, make sure you have the absolute value is equal to 2. Yes, in theory, you could probably just say plus or minus 2 at the end, but I usually like doing this because I've got a method which we'll play around with here in a minute. We can also make this lambda minus 1 because it's interchangeable at this point. Right, factor out a negative, and we take the absolute value of that negative. So here we get lambda is going to be 1 plus or minus 2, so yeah. What you said before.
So that actually will tell me that these are going to be real solutions, and the sine tt will be linearly independent, which is nice.
Yeah, just real quick for anybody who was curious, my method for this is like a pseudo graphical one. I do it on stream all the time, but we'll just real quick, because it's fun. I say that the difference between the number we're trying to find, lambda, and the number that's going to serve as an anchor point which is 1. I use the absolute values as a distance measurement, and so here we're saying that the distance, or the difference, between 1 and lambda, the thing we're trying to find, is 2. So that means that we travel a distance of exactly 2 in either direction, and we find where our solutions are. So upwards is 3, downwards is -1. Since it's just equal, then we want those particular numbers and no others. This also works very nicely for inequalities, because then you could say if it's less, then you need to be less of a distance away from those maximum points. And if it's greater than, you need to be further away than those particular border points. So I make a little graph out of it, and I don't know, pre-calc students seem to like it. Again, mostly because it's like showing them something that they're not used to. I think generally for pre-calc especially, that's something that we need to get into the habit of doing. Okay. So we get our null space solution is going to start with C1. We have a vector which we don't know yet, and then e to the -t. Plus C2 unknown eigenvector e to the 3t. Right, and they are also linearly independent of G, which you said earlier. Okay. And then to get the rest of the null space solution, we have to find the eigenvectors. How are we doing that one?
Same thing with using the eigenvector or eigenvalues, put them in to the matrix you made above with the lambdas and so on.
Right, and augment with 0, 0. So when lambda is -1, we're going to get a 1 minus lambda 1, 2, 2, 1 minus lambda 1, -1, augment 0, 0. So we get a 2, 2. And then in the lowercase, we can also say take row row 2, come on, minus row 1. And then put it into row 2, so we just get zeros. Alright, what does that produce for us?
Well, it says that the eigenvector is going to be 1, -1. Because we can say this is a linear system. 2x2 plus 2x1 plus 2x2 equals 0, and so we have 1, -1. And C2, the V2, this eigenvector 2, is going to be similar. We just put in lambda equals 3 rather than -1.
So 1 minus 3, 2, augment 0, and 2, 1 minus 3, augment 0. So -2, 2, 0. And 2, -2, 2, 0. Okay, so again, row 1 plus row 2, store into the bottom one is just going to get us 0, 0, 0. And what's that proving for us?
So that demonstrates that our eigenvector is 1, 1.
Yeah. And whether we change all that stuff or not doesn't much matter. Again, this is going to be -x1 plus x2 is equal to 0, or then x1 is equal to x2, right? And if they're going to be equal to each other, the simplest version we can make is going to be 1, 1. All right, null space done. Now what?
And then I'm gonna need to get going.
That's fine.
We just hit the 4 o'clock mark for us. And I'll probably be lurking in other chats as well. Just
oh yeah,
because that's like I'll be doing other stuff today, but but it's good to be here, and I'm glad I was able to help out a little.
Yep. Thanks, Zach.
Yeah, no problem. Thank you.
Anything you want to?
No, I mean I think this is gonna be interesting. I guess where are we going with this content?
Yep.
On
so,
Wednesday?
In the next couple classes, we are going to talk a bit about locally linear systems.
Okay.
And we are going to bring all of this stuff back to second-order differential equations, and how all of these methods kind of can inform how to do second-order linear differential equations, rather than, as most of the differential equations classes do, start with first order and then just run to second order and like come up with all these crazy methods.
Cool. All right. Very good.
Alrighty.
I'll see you on Wednesday.
Yep. Thanks so much.
Barring any complications, yeah.
Oh yeah.
Yeah. All right.
See you
We'll
later.
Yep.
Alrighty. So then we're going to ad break. Alright, everybody's back. Sorry about that. Yeah, when I'm really in the zone here, it also didn't pop up until it was too late, so like it already started the ad. Anybody who didn't catch that, Zach will be in other chats and things like that, so you can see him around with other channels that we have. Most of the time it's science communication, math communication, but as with anyone, you know, depending on how the mood is and whatever else, might pop into some other people's channels too. So, what we're going to look at is finding the particular solution for this differential equation. And then once we get to the end of that one, I think we'll probably call it a night. Can we do it in the next 20 some odd minutes? Probably. I want to thank everybody for sticking around and for coming into the channel. Sugway, thank you so much for following, and everybody else for stopping in and saying hi. Do we have our... Yeah. We're up to 472 followers. That's pretty awesome. We're working on the path to 500. So if you know any friends who want to learn some math content, send them on over. Alright. So what we're going to say is now we've got our multiple different ways to find the particular solutions. I would say in this particular case, what we would like to do is to take our particular solution and say that we had an A vector times, that's the vector, I don't need another vector here, times sine of t. Plus a b vector times t. So linear function and a sine function. We did not have anything of either of those types in our non-homogeneous solution, being e to the negative t and e to the 3t. So having sine of t and t is perfectly acceptable. So with that, we want to then say, assuming that this is our solution, or at least this is what the solution is generally going to look like, then we want to plug in this particular solution, x sub p, into our into our original function, our differential equation up top. So again, if we ended up with putting our two pieces together, so having both our both our null space solution and our particular solution together, then the null space solution shows up on both sides and drops out, leaving behind everything that we're going to do here. So this was 1221 times the quantity. Alright, we'll stop the share here because this will hopefully speed it up a bit. A vector